this lecture onwards, we will be starting a new topic, which is deadlocks. So this is a new chapter, and also this is a very important chapter in operating system. So we will be understanding what are deadlocks, what causes deadlocks, what are the problems that occur due to deadlocks, and how deadlocks can be avoided. So in the previous chapter of process synchronization, we have also come across this term deadlocks. So this must not be a new term for you if you have studied that previous chapter. So in this chapter, we will be discussing from the beginning what are deadlocks, and we will be understanding from scratch, and we will be discussing all the details. Alright, so let's move ahead. So we know that in a multi-programming environment, several processes may compete for a finite number of resources. So we have already discussed about what are the resources. A computer system may be having a lot of resources, like for example, CPU, memory, input-output devices. These are all known as resources. So in a multi-programming environment, we know that there are several processes involved, and these several processes may be competing for a number of resources. So a process requests resources, and if the resources are not available at that time, the process enters a waiting state. So we said that there are several processes in a multi-programming environment which are competing for certain resources. So when a process needs a resource, it will request for that resource, and if the resource is available, the resource will be given to that process and it will be using the resource. But what if the resource is not available at that time? And by not available, what do we mean? A resource may not be available when that particular resource is currently being held by some other processes. So at that time, when a requested resource is not available, so what happens? The requesting process will enter a waiting state. So it will wait until and unless it gets that resource to continue its execution. So sometimes a waiting process is never again able to change state because the resource it has requested are held by other waiting processes. So in some cases, when a process requests for a resource, it enters the waiting state because the resource is not available, as we have just discussed. And sometimes it will never be able to change from its waiting state because the requested resource is being held by other processes and it is not being released. So the process keeps on waiting and it is not able to come out of its waiting state. And also let's say that the process that is currently holding the resource is also waiting for some other resource that is being held by some other processes. So this cycle may go on, and at this time we enter a state where the processes are waiting for each other to release the resource, but everybody is waiting for each other, and hence nobody is able to continue from their waiting state and they are stuck in that state. So this situation is called a deadlock. So this is the basic idea of a deadlock. This is when a deadlock occurs. So in order to explain in a simple everyday terms, let's say that there are two trains that needs to pass through a crossing like this. So we see that there is a crossing like this and two trains are approaching to the crossing. So we know that when one train is crossing the lane, the other train has to wait. So let's say that both these trains come and they wait at these points. And what happens is, this first train is thinking that I will wait for this train to cross, and after it crosses, I will cross. At the same time, this second train is thinking that I will wait for this first train to cross, and after that, I will cross the lane. So we see that both of them are waiting for each other. This train is waiting for this, and it will only cross after this one crosses. And at the same time, this train is waiting for this train to cross, and only after this one crosses, this will cross. So we see that both of them end up waiting for each other, and eventually nobody is going to cross and they are both going to be in a waiting state, stuck there forever. So this is just a classical example of a deadlock. So this will not occur in real life with trains, but this is just an example that we have taken in order to make us understand what is a deadlock. Alright, so now we will be trying to understand the system models in which our systems work, so that we can have a clear understanding of how deadlocks occur and the other details of deadlocks. So here we will be discussing about the system model. So a system consists of a finite number of resources to be distributed among a number of competing processes. So this is the first thing that we have discussed in the beginning of this lecture itself. So we have different processes competing for various number of resources in a system. And in a system, there is a finite number of resources which can be distributed among the competing processes. And then the resources are partitioned into several types each consisting of some number of identical instances. So we have several number of resources which are partitioned into several types, and each of these resources may have number of identical instances. So for example, let's say that CPU is a resource. So we may not be having just one CPU. We may be having multiple instances of CPU. So let's say that we are having two instances of the CPU. So if we are having two instances of the CPU, two processes will be able to use the CPU at the same time because there are two instances. So when one process requests for the CPU, it will get one of the instance of the CPU. When the other process requests for the CPU, it will get the other instance of the CPU. So likewise, there can be several identical instances of different resources, and they can be distributed among the processes that are competing to get them. So here are some examples of resource types. So we have memory space, which is a resource that can be used by processes. We have CPU cycles, which we were just talking about now. Then we have files, and we have input-output devices like printers, DVD drivers, etc. So these are the examples of resources. And each of these resource types can have identical instances. They may have several identical instances of each of these resources. And depending upon the number of instances they have, they can be distributed among the competing processes. So we have understood the system model. Now let's see, when a process needs to utilize a resource, what is the sequence that it has to follow in order to make use of the resource? So under a normal mode of operation, a process may utilize a resource in only the following sequence. So let's see what is that sequence. So in this sequence, the first step is request. So when a process needs to get hold of a resource, it needs to first request for that resource. So if the request cannot be granted immediately, for example, if the resource is being used by another process, then the requesting process must wait until it can acquire the resource. So, as I already told you, the process will request for the resource, and if the resource is available, then the resource will be given to that process and it can use it. But if the request cannot be granted immediately, and why does that happen? It happens because the resource may be held by some other process. So at that time, what it must do, the requesting process must wait until it can acquire the resource. And how long will it wait? It will wait until and unless the process that is currently holding the resource will release it. Until then, it has to wait. So the first step is to request. And the second step in our sequence is to use. So obviously, the process can operate on the resource. For example, if the resource is a printer, the process can print on the printer. So this is very obvious. The second step will be using the resource. So once the process gets hold of the resource, it can just use the resource. So here an example that we have taken is a printer. So printer is also a resource. It is an output device. And if a process is requested for the printer and if it is available, then the process can make use of the printer. So that is the second step. Now let's see what is the third and the final step. So the third and the final step in our sequence is to release. So the process releases the resource once it completes its utilization of the resource. So once the process completes its usage of the resource, it cannot hold on to that resource forever. It has to release it because other processes will want to make use of the resource. So after it makes use of the resource, it has to release it. So these are the simple three sequence steps that a process has to follow when it needs to utilize a resource: request, use, and release. So this is another important thing that we need to keep in mind when we are going to start studying about deadlocks. So here let's take an example of how deadlocks could occur. So here in this example, let's say that we have three processes, P1, P2, and P3, and let's say that we have three CD read and write drives. So these are three CD read and write drives. So these are three resources. So each of this process may want to use these resources. So let's say that currently each of the processes wants to make use of one CD read write drive. So here we see that there are three processes and we have three resources and they can be easily distributed among the three of them. So no problem. Process P1 gets hold of the first CD read write drive, process P2 gets hold of the second one, and process P3 gets hold of the third one. So they are happily using the resources without any problem. Now let's say that another scenario occurs here. Each of these processes now wants to use one more CD read write drive. That means they not only want one, but each of them now needs to use two CD read write drives. So at this moment, what happens? We still have only three of these drives. Now how can they be distributed among these three processes? Now let's see what happens here. So if such a case occurs, we see that processes P1, P2 and P3 are still holding the resources that they were already holding. So this blue line represents the resources that they are already in hold of, and these yellow lines, they represent the request they are making in order to make use of some other resources. So here we see that processes P1, P2 and P3, they are already holding these CD drives 1, 2 and 3 respectively. Now, we said that a case has occurred when all the processes needs one more drive. So what happens? Process P1, let's say it requests for this drive, and process P2 is requesting for this drive, and process P3 is requesting for this drive. So when we studied about the sequence that a process has to follow for utilizing resources, we know that the first step is to request. So they are requesting these drives now. Now let's see what happens. P1 is requesting for this drive, but what happens? This drive is already being held by P2, and P2 is not going to release this drive now because P2 also is now requesting for another drive, which is this one, and this drive is already being held by P1, and P1 will also not release it until and unless it gets this drive which it requested and completes its operation. Until then, it is not going to release the drive that it is holding. And P3 also similarly, it also wants one more drive and it has requested for this one. And this one is being held by P2. And P2 is not going to release it until and unless P2 gets the drive that it requested for, which is this one. Now we see that they are all not going to release the drive until and unless they get the other drives that they have requested. And hence they are going to all keep waiting for each other, and this is known as a deadlock. So here a deadlock has occurred. So these processes right here, they are going to keep waiting for these resources, and these resources will not be released because they are waiting for each other to release the resources. So we see that in this condition, these processes P1, P2 and P3 are going to be stuck in this state forever. So this condition is known as a deadlock. So we read right. So in the first case, let's say that P1 just wants to use the printer and it is using the printer, and P2 just wants to use the CD read-write drive and it is just using that. Now let's say another case has occurred when process P1 wants to make use of the CD read-write drive and P2 wants to make use of the printer, but they have not released the resources that they were already holding on to. is using the printer, and P2 just wants to use the CD read-write drive and it is just using that. Now let's say another case has occurred when process P1 wants to make use of the CD read-write drive and P2 wants to make use of the printer, but they have not released the resources that they were already holding on to. So let's see, process P1 is holding on to the printer, and before it releases the printer, it wants to make use of the CD read-write drive, and it is requesting for that. And at the same time, process P2 is holding the CD read-write drive, and also at the same time, it needs to make use of the printer, and hence it is requesting for the printer, which is being held by process P1. Now, we see that P2 will not release this CD read-write drive until it gets the printer, and P1 will not release this printer until it gets this CD read-write drive. So here again in this case, both these processes are going to end up waiting for each other to release the resources that they are holding, and they are not going to release it until the other one releases it. So they are going to end up waiting for each other, and hence this is another situation of deadlock. So this is the example of deadlock which can occur with different kind of resources. So we see that when this kind of scenarios occur, the processes are going to get stuck and they are not going to move ahead. And obviously this is a very bad thing for our computing because processes are getting stuck. So we need to avoid this. So this chapter will be dedicated for understanding deadlocks and also seeing how deadlocks can be prevented. So with this chapter, which is an introduction to the deadlocks, I hope you have got a basic idea of what deadlocks are. So in the following lectures, we will be going into more details of deadlocks, and we'll also be seeing how deadlocks can be prevented. So I hope this lecture about deadlocks was clear to you. Thank you for watching and see you in the next one. Lecture, we have started studying about deadlocks, and we have seen an introduction to deadlocks, and we have seen basically how deadlocks occur. So in this lecture, we'll be studying about deadlock characterization. So that means we are going to discuss about the features that characterize deadlocks, and we will be seeing what are the necessary conditions that must hold for a deadlock to occur. So we have already seen that in a deadlock, processes never finish executing and system resources are tied up, preventing other jobs from starting. So when we have started discussing about deadlocks itself, we have seen this. So we know that a deadlock occurs when a process is waiting for a resource that is being held by some other process, and even that process in turn is waiting for some other resource which is also held by some other processes. So hence we see that they keep waiting for each other, and hence they never finish their execution, and then the system resources are tied up, preventing other jobs from starting. So the processes are holding the resources and they are not releasing it because they are in turn waiting for some other resources. So we see that processes never finishes their execution, and also resources are tied up and are not available for use for other processes. So this is what happens in a deadlock. So now we will be seeing the features that characterize deadlocks. That means the necessary conditions that must hold for a deadlock to occur. So we'll be discussing 4 conditions here. So it says here that a deadlock situation can arise if the following 4 conditions hold simultaneously in a system. So we'll be seeing 4 conditions, and for a deadlock to occur, these 4 conditions must hold simultaneously in a system. So if they hold simultaneously in a system, we can say that there will be a deadlock. So let's see what are those conditions. So the first condition that we have is mutual exclusion. So mutual exclusion is not something new. We have already come across mutual exclusion many times in our previous lectures. Actually, all these 4 conditions that we are going to discuss are not going to be new terms, but they are terms that we have already seen in some of our previous lectures. But we need to know this even clearer in order to understand deadlocks in a better way. So let's see. So what is mutual exclusion? So it says here that at least one resource must be held in a non-shareable mode. That is, only one process at a time can use the resource. If another process requests that resource, the requesting process must be delayed until the resource has been released. So we already know that in mutual exclusion what happens is there is a resource that is held in a non-shareable mode. That means if one process is holding that resource, then no other process can take that resource away from that process until and unless the process holding the resource releases it by itself. So here we use the term non-shareable mode. That is because the resource that is there cannot be shared by two or more processes. It can be used only by one process at a time. So when that process is using the resource, if another process wants to use that resource, then what will happen? That requesting process must be delayed until when? Until the resource has been released by the process that is currently holding the resource. So this is what we mean by mutual exclusion. So if there is mutual exclusion, then we see that we have one of the conditions that must be there for a deadlock to occur. Alright, so that was the first condition, which is a necessary condition that must be there for deadlock to occur. Now let's see what is the next condition. The next condition that we have here is hold and wait. So let's see what is this. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. So from the name itself, we can try to understand hold and wait means one process is holding a resource and at the same time, it is trying to acquire another resource that is currently being held by another process. So the process is holding the resource and also it is waiting for another resource which is being held by some other process. So this is another condition. So this also we have seen when we have discussed about deadlock in the previous lecture. A process was holding a resource and it is also trying to get hold of some another resource which is being held by some other processes. So that is what we mean by hold and wait. From the name itself, it's easy to understand. A process is holding the resource and it is waiting for some other resource which is being held by another process. So this is another necessary condition that must be there for a deadlock to occur. Now let's see what is the third condition. So the third condition that we have is no preemption. So again, preemption is also not a new term. We have come across this. So let's see what it says. Resources cannot be preempted. That is, a resource can be released only voluntarily by the process holding it after that process has completed its task. So we have already come across this term preemption. And what does preemption mean? So let's say that one process is making use of a resource and at that time another process wants to make use of that same resource and it takes away that resource away from the process that is currently holding it even before it finishes its execution. That is called preemption. When a resource can be taken away from a process even before it finishes using the resource, that is what we mean by preemption. But for deadlock to occur, there should be no preemption. We cannot allow preemption. So resources cannot be preempted. A resource, if it is being held by a process, can be released only by that process voluntarily and no other process can come and take it away from it until and unless that holding process voluntarily releases that process by itself. So that is what we mean by no preemption. So this is also another necessary condition that must be there for a deadlock to occur. Now let's go to the fourth and the final condition that we have. So the fourth and the final condition that we have is circular wait. So it says here, a set P0, P1 up to Pn of waiting processes must exist such that P0 is waiting for a resource held by P1, P1 is waiting for a resource held by P2, and it goes on in that way. Pn minus 1 is waiting for a resource held by Pn. And even this will not end, this will also go on. Pn may be waiting for some other resource that is held by some other processes behind that. So it forms a circular waiting. So here P0, P1 up to Pn, they are processes that we have. And we see that P0 is waiting for a resource which is held by P1. And P1 is waiting for a resource which is held by P2, and it goes on like that, such that Pn minus 1 is waiting for a resource held by Pn, and even this Pn may be waiting for a resource that is being held by some other processes behind this. So in that way, we see that there is a circular waiting pattern that is formed. They are waiting for each other in a circular fashion. So this is also another necessary condition for a deadlock to occur. So we see that the circular wait is also almost similar to the hold and wait. Here also, a process is holding one resource and is waiting to acquire additional resources being held by other processes. So in circular wait also, we see the same thing happening, but we just see that they are waiting in such a way that they wait in a circular fashion. So that is what we mean by circular weight. So these two are actually dependent on each other, this hold and weight and circular weight. So this was the final and the fourth condition that must be there for deadlocks to occur. So let's just summarize what we have studied. The four necessary conditions that must hold for a deadlock to occur are mutual exclusion, hold and weight, no preemption, and circular weight. So we emphasize that all four conditions must hold for a deadlock to occur. So all these four conditions must hold, and then we can say that a deadlock can occur. And the circular weight condition implies the hold and weight condition. So the four conditions are not completely independent. So I already showed you how the circular weight and the hold and weight are similar to each other. So if we take a closer look, we can understand that these four conditions are not independent of each other. They are somehow dependent on each other. So these are the four necessary conditions that must hold for a deadlock to occur. And these are the features that characterize a deadlock. So these are things that we need to keep in mind when we are studying about deadlock, and this will help us to understand deadlock as we move ahead. So I hope this lecture about deadlock characterization was clear to you. Thank you for watching, and see you in the next one. For a deadlock, in this lecture, we'll be studying about a resource allocation graph. So we have been studying about deadlocks, and we have seen some introductions and the basic characterizations of deadlocks, and we have also seen the necessary conditions that must hold for deadlocks to occur. So now we will be seeing the resource allocation graph. So this resource allocation graph is a pictorial representation of processes and resources, and how processes are holding resources and how resources are allocated to processes. So using this graph, we will be trying to understand if there is a deadlock in the system. So as I said, deadlocks can be described more precisely in terms of a directed graph called a system resource allocation graph. So this is an important topic under deadlocks. You should be knowing how to form resource allocation graphs, and you should also be knowing how to read resource allocation graphs. That means by seeing the graph, you should understand what it means, and you should be able to understand if there are deadlocks in the system by seeing the graph. So we will be seeing what is this resource allocation graph, how it is formed, and how we can understand it. Alright, so let's go ahead. So this graph consists of a set of vertices V and a set of edges E. So in this resource allocation graph, we'll be having a set of vertices V and a set of edges E. And let's see what are the vertices and the edges. So the set of vertices V is partitioned into two different type of nodes. So we said we are having a set of vertices and edges. So first we are going to talk about the vertices. So these vertices are partitioned into two different type of nodes. And what are they? The first set is P. P denotes the set consisting of all the active processes in the system. So P is the set of processes that we are discussing about in the system. So we have in this set P1, P2 up to Pn, which denote the processes in the system. So we have up to n, so which denotes that there are n active processes in the system. And then the next set that we have is R. So R denotes the set consisting of all resource types in the system. So R is the set that denotes the resource types in the system. So here we have R1, R2 up to Rm, denoting that M is the total number of resources that we have in the system. So this is how the vertices V is partitioned into two different type of nodes. The first set is the processes and the second set is the resources. So here the processes, as we know, will be wanting to make use of the resources, and the resources has to be allocated to the processes. So how it is done, how it is depicted, we will be seeing as we move ahead. Alright, so we talked about the vertices. Now let's talk about the edges in this graph. So again, there will be two type of edges in this graph. So let's see what they are. The first kind of edge is called a request edge. And what is a request edge? A directed edge from process Pi to resource type Rj, which is denoted like this, signifies that process Pi has requested an instance of resource type Rj and is currently waiting for that resource. So a request edge is represented like this, Pi, and there is an arrow going to Rj, which means that the process Pi is requesting for an instance of the resource Rj, and it is currently waiting for that resource. So now I am saying instance of the resource. So why I say this is because a particular resource may have different instances. So I've already talked about it in the first lecture of deadlocks. So I told you that a resource can have different instances. For example, there may be a resource called CPU, and there may not be one CPU but two CPUs, two instances of the CPU. So every resource may have one or more instances. So whenever you see an edge like this with Pi pointing to Rj, it means that the process Pi is requesting for an instance of the resource type Rj, and it is currently waiting for that resource. So when you see an arrow like this, remember that it is requesting as well as it is waiting for the resource. It has not got that resource yet, but it is waiting to get the resource. So that is the first kind of edge that we have. It is called the request edge. So request edge will always be pointing from the process to the resource like this. Alright, so let's see now what is the second type of edge that we have. So the second type of edge that we have is known as the assignment edge. So what is this? A directed edge from resource type Rj to process Pi, which is represented like this, signifies that an instance of resource type Rj has been allocated to process Pi. So in assignment edge, you will see that the arrow points from the resource to the process. So what does it mean? It means that an instance of the resource type Rj has been now allocated to the process Pi. So this is known as the assignment edge. So at this moment, the resource Rj or an instance of the resource Rj is being held by the process Pi. So this is what we mean by assignment edge. So in request edge, the process is waiting to get the resource. It has requested and it is waiting. And in assignment edge, the resource has been allocated to the process. So the process is holding the resource. So in assignment edge, you will always see that the arrow goes from the resource to the process. So keep this in mind. So these are the two type of edges that we have, the request edge and the assignment edge. Alright, so now we have understood the vertices and the two type of vertices, and also the edges and the two type of edges. Now let's see how we can draw a resource allocation graph. So in order to draw a resource allocation graph, we should first know the shapes that we have to follow. So first we have the circle. And what is a circle? Processes are represented using circles. So whenever you see circles, know that they are processes. So even when you are forming it, always use circles to represent processes. And then we have these rectangles. So what are the rectangles? Resources are denoted using rectangles. Since a resource type Rj may have more than one instance, we represent each such instance as a dot within the rectangle. So resources are denoted using the rectangle. So whenever you see rectangles, understand that they represent resources, and even when you are forming it, make sure that you always use rectangles to represent resources. Now, as I already told you, each resource may have different instances of the same resource. So we are having these dots inside the rectangle to represent the instances of a particular resource. So here in this rectangle, we see there are three dots, which means that there are three instances of this. Since a resource type Rj may have more than one instance, we represent each such instance as a dot within the rectangle. So resources are denoted using the rectangle. So whenever you see rectangles, understand that they represent resources, and even when you are forming it, make sure that you always use rectangles to represent resources. Now, as I already told you, each resource may have different instances of the same resource. So we are having these dots inside the rectangle to represent the instances of a particular resource. So here in this rectangle, we see there are 3 dots, which means that there are 3 instances of this same resource. So let's say that this resource represents a CPU. So 3 dots inside this rectangle will mean that there are 3 instances of the CPU. Hence, 3 different processes can use this resource at the same time because there are 3 different instances. So this is how you will be representing resources using rectangles and the dots to represent the instances of that particular resource. Alright, so now we have understood most of the things that we need to form a resource allocation graph. So let's take an example of a resource allocation graph and see how we put all these things together and how a resource allocation graph looks like. So here is an example of a resource allocation graph. So this is how a resource allocation graph looks like. So here we see that we have circles which represents the processes. So we have 3 processes here, P1, P2 and P3. And here we have these rectangles that represents the resources. So we have 4 rectangles here, R1, R2, R3 and R4. So we have 4 resources and we see there are dots inside these rectangles which represents the instances of that resource. So we see that resource R1 is having just 1 instance, R3 is also having 1 instance, resource R2 is having 2 instances and resource R4 is having 3 instances. So these are the things that we have here. Let's see what are the sets. P consists of the set of processes, P1, P2 and P3. R consists of the set of resources, R1, R2, R3 and R4. And then here in this set, we are representing the edges. We have talked about the assignment edge and the request edges. So let's see how it is shown here. So if you look at this process P1, you see that there is an arrow going from process P1 to the rectangle R1. That means this process P1 is requesting for an instance of the resource R1. So we see there is a request edge here, P1 to R1. P1 is requesting for the resource R1. And we also see there is a request edge from P2 to R3. So you see this is P2. P2 is requesting for a resource type R3. So there is a request edge going here. And then we see that there is an assignment edge here from R1 to P2. So whenever it is an assignment edge, it will start with the resource. So let's see, R1, where is R1? This is R1. And you see that an instance of the resource R1 is being allocated to P2, the process P2. So this is an assignment edge. The arrow is coming from the resource to the process. And here we see there is another assignment edge from R2 to P2. So this is R2 and we see that one instance of R2 is being assigned to the process P2. And similarly, there is another instance of R2 being assigned to P1. So you see, R2 is having 2 instances. So 2 processes can make use of R2. So this second instance of R2 is being allocated to the process P1. So that is what is represented here. And then R3 to P3. So this is another assignment edge. The resource type R3, this instance of R3 is being assigned to the process P3. So these are the assignment and the request edges that we have in this resource allocation graph. And these are the resource instances which I've already told you. There is one instance of resource type R1. There is only one dot in R1. That means there is only one instance of R1. And there are 2 instances of resource type R2. So if you see R2, there are 2 dots inside R2. So that means there are 2 instances. And again, one instance of R3, we see that here. And 3 instances of resource type R4. So this is R4 and it is having 3 instances. And you see there are no arrows coming to R4 or going from R4. That means that nobody is actually making use of R4 right now. And another thing that you need to keep in mind while drawing this graph is that whenever it is a request edge, that is the edge going from the process to the resource, you will be drawing the arrow from the circle of the process to the outer part of the rectangle. Don't make it go inside the rectangle, but just let it touch the rectangle at one of its sides. And why do I say this? This is because in a particular resource, we know that it could have multiple instances. So when a process is requesting for a resource, we don't know which of the instance of the resource will be assigned to that particular process. So don't make this request edge arrow point up to the dot, but only make it point up to the rectangle. But when you are making an assignment edge, always make sure that the arrow starts from the dot and goes to the process circle. Because in an assignment edge, we know that there will be a particular instance that will be assigned to a particular process. So in an assignment edge, always start from the dot. But when it is a request edge, start from the process and touch only till the outer part of the rectangle. So if you look at this R2, resource R2, we see that there are two instances. So we see first instance is going to P2 and the second instance is going to P1. So this is how it is assigned. So we see we should start the arrows from inside the rectangle from the dots. But when processes are requesting for instances, we should only make the arrow go up to the side of the rectangles so that it shows that the process is requesting for an instance, but which instance will be assigned to the process that we do not know at that time. So that is another thing you have to keep in mind. So this is how a resource allocation graph looks like. So how do we find out if there are deadlocks in a system using the resource allocation graph? So the first and foremost thing that you need to remember is that if there is a deadlock, then in the resource allocation graph, you will be able to find a cycle in the graph. So what do we mean by cycle and how can we identify a cycle? So a cycle is something like you start from a particular process and then you follow the arrow, and if the arrows lead you back to the same process or the same place where you have started, then that is called a cycle. Like for example, here you see that P1 goes to R1 and R1 is going to P2, and from P2 it is going to R3, and from R3 it is coming to P3, and from P3 it's not going anywhere. So here we cannot say that there is a cycle. There is no cycle here. So in this particular resource allocation graph, we can say that there is no deadlock occurring in this system. But if there is a cycle, there is a chance that there will be a deadlock. And again, keep in mind that if there is a cycle, it doesn't necessarily mean that there will be a deadlock for sure. But there can be a possibility that there can be a deadlock. So to make this clear, let's take two more examples. So as I told you, if the graph contains no cycles, then no processes in the system is deadlocked. So if there is no cycle in the graph, we can be sure that there is no deadlock in the system. But if the graph does contain a cycle, then a deadlock may exist. So if there is a cycle in the graph, then a deadlock may exist. So I am emphasizing on this word may, because it is not sure that a deadlock will exist, but there is a possibility that there could be a deadlock. So just having a cycle is not a sufficient condition for a deadlock, but it is a necessary condition for a deadlock. That means if there is a deadlock for sure, there will be a cycle for sure. But just because there is a cycle doesn't mean that there will be a deadlock for sure. So you will understand that when we take the following examples. So here is an example. So here we have the same example that I took from above, but I have added one more edge here. So we have these same processes P1, P2, P3 and resources R1, R2, R3 and R4 with the instances of resources also same like the previous example. But now I have added one more edge, that is from P3 to R2. Now, are there any cycles in this system? So at this point, two minimal cycles exist in the system. So let's see what are these cycles. So if you start from process P1, P1 is going to R1, and from R1 it comes to P2, and from P2 is going to R3, and from R3 it is going to P3, and P3 is going to R2, and R2 is going back to P1. So we came back from where we started. We started with P1, and we came back at P1 itself. So that is what we mean by a cycle. So also if we start from P2, let's see, from P2, the arrow is going to R3. From R3, it is coming to P3. From P3, it's coming to R2. and from R2 it is coming back to P2. So we started from P2 and we ended at P2 again. So that is a cycle again. So two minimal cycles exist in the system now. And if this kind of a cycle exists, then that means that the processes P1, P2 and P3 are deadlocked. Now let's take a closer look and see what actually happened here. So P1 is requesting for resource type R1, which is having only one instance, and that is being held by P2. And P2 is requesting for R3, which is also having only one instance, and that instance is held by P3. And P3 is asking for R2, and R2 is having two instances, but both these instances are being held by either P1 or P2. So if we go in this direction, we see that this instance of R2 is held by P1. So we are coming back here, and what will happen if we go like this? We are going to continue going like this in this cycle. This cycle is not going to end. And even if we go from here also, this cycle is going to continue and it is not going to end. So we see that the processes are waiting for resources which are being held by other processes, and nobody is going to be able to release the resources because they are waiting to acquire other resources. So this cycle is not going to break and they are going to be stuck in this cycle, and hence we say that the processes P1, P2 and P3 are deadlocked. So this is how you can identify whether deadlocks will be occurring in a system using the resource allocation graph. So again, I said that if there is a cycle, a deadlock may exist. So this is a condition or an example where there is a cycle and the deadlock actually existed. Now let's take another example. So here we have another example. This is another one. Here we have four processes, P1, P2, P3 and P4, and we are having two resources, R1 and R2, and both of them are having two instances each of the resource types. Okay, R1 is having two instances, R2 is also having two instances. So in this example also we have a cycle. Let's see what is a cycle. We see that P1 is waiting for resource R1, and R1 is being held by P3, and P3 is waiting for resource R2, and R2 in turn is being held by P1. So we see that we started from P1 and we ended back at P1 again. Started at P1 and we ended at P1. So obviously there is a cycle in this system. But is there going to be a deadlock here? However, there is no deadlock here. And why do I say there is no deadlock? Observe that process P4 may release its instance of resource type R2. That resource can then be allocated to P3, breaking the cycle. So what do we mean here? Let's follow the cycle again and see. P1 is requesting for R1, but R1's both instances are held by P2 and P3. So let's go in this way, P3. So R1 is being held by P3, and then P3 is asking for R2, and R2 is having two instances. One of the instances is held by P1 and the other instance is held by P4. So if we go like this, we see there is a cycle. But if you observe, you see that this process P4 is holding the resource R2, and this process P4 is not asking for any other resource. It is not requesting for any other resource. So once P4 completes its execution, it is going to release this R2. So when P4 is going to release this R2 can be assigned to P3. So P3's request will be granted, and hence this arrow will not come like this anymore, but then there will be an arrow going from this resource to P3. So there will be no cycle anymore. That cycle will be broken, and hence there will be no deadlock. So in this example, we see that though there is a cycle, there is a possibility that there will be no deadlock because of this process P4, which will release the resource R2, and hence this will be assigned to P3 and there will be no cycle after that. So this is an example where we see that though there is a cycle, there is no deadlock. So that is why I said that when there is a cycle, it is not sure that there will be deadlock, but there is a possibility that there is a deadlock. So a cycle is a necessary condition for a deadlock. That means if there is a deadlock, there will be a cycle for sure. But it is not a sufficient condition. That means just because there is a cycle doesn't mean that there will be a deadlock for sure. Because resources may have multiple instances, and just like this example, we see that the cycle could be broken and hence there will be no deadlock. But there is another case where each of the resources are having only one instances. So what will happen if there is a cycle in such a system? Then there will be deadlock for sure. So if there is a cycle in a system where each of the resources have only one instance each, then just by seeing that cycle, you can say that there will be a deadlock for sure. But if there are multiple instances like this, we cannot be sure. You have to analyze it further and then find out if there will be a deadlock. So this is how you can analyze and identify deadlocks using a resource allocation graph. So keep in mind how we form this graph. Circles represent processes, rectangles represent resources, dots inside rectangles represent the instances of resources, and then the arrows going from processes to the resource denotes request edge, and the arrows coming from the dots inside the resources to the processes denotes the assignment edge. So this is a request edge, and when the request is granted, it will be converted to an assignment edge. So the arrow will be in the opposite way. So these are the things that you need to keep in mind. As a summary, we can say that if a resource allocation graph does not have a cycle, then the system is not in a deadlock state. But if there is a cycle, then the system may or may not be in a deadlock state depending upon the conditions that I have explained to you. So these are the things that we need to keep in mind in a resource allocation graph. So this is an important topic under deadlocks. You should be knowing how to form resource allocation graphs, and also you should be able to read and understand resource allocation graph and be able to identify deadlocks from resource allocation graphs. So I hope this lecture about resource allocation graph was clear to you. Thank you for watching, and see you in the next one. In this lecture, we'll be studying about resource allocation. In the previous lectures, we have been studying about deadlocks, and we have seen how deadlocks occur in a system, and we have also seen what are the types of deadlocks that can be there. And we have seen clearly that deadlock is a problem. And so in this lecture, we will be discussing about the methods for handling deadlocks. So we'll be seeing how we can handle deadlocks, and we'll be seeing the different methods that we have which can be used for handling deadlocks. So we can deal with deadlock problem in one of the three ways. So we'll be discussing three methods here using which we can handle deadlocks. So we'll be seeing this in brief in this lecture, and then in the following lectures we'll be discussing each of these methods in detail one by one. Alright, so first let us see what are these three ways that we can use for handling deadlocks. So the first method is we can use a protocol to prevent or avoid deadlocks, ensuring that the system will never enter a deadlock state. So the first method or the first way is prevention. So we have always heard the phrase prevention is better than cure. So in the same way, here we are trying to make sure that the deadlock does not occur in the first place itself, so that we don't need to deal with deadlocks later on. So what we are going to do here is we are going to use some protocols to prevent or avoid deadlocks. We will be trying to prevent or avoid deadlocks from happening in the first place itself, ensuring that the system will never enter a deadlock state. So if we can prevent it in the beginning itself, so we don't have to deal with it in the future. So this is the first way that we can use for handling deadlocks. And the second way is we can allow the system to enter a deadlock state, detect it, and recover it. So unlike the first method, in the second method, we are allowing the system to enter a deadlock state. That means we are not preventing it from the beginning, but if a system enters a deadlock state, we are going to detect it and we are going to recover it. So here we are not preventing, but we allow the system to enter a deadlock state. But we are making sure that if the system enters a deadlock state, we should be having a mechanism to detect that, yes, the system has entered a deadlock state. And also we have to make sure that we have some methods to recover from the deadlock. So this is another way of handling deadlocks. And the third and the final way is we can ignore the problem altogether and pretend that deadlocks never occur in the system. So in this third way, we are not trying to prevent or avoid deadlocks, nor are we having any mechanism to detect and recover from it. We are just ignoring the problem altogether, and we just pretend that deadlocks will never occur in the system. So you may be thinking, what kind of a strange solution is this? So though this looks like a strange solution, this method is also used by many of the operating systems. So in this method, it is not the responsibility of the operating system to deal with deadlocks, but it is the responsibility of the application programmers to program and develop their applications in such a way that the processes do not enter a deadlock. So it is their responsibility and not the responsibility of the operating system. So this is also a method for handling deadlocks, even though it looks like a strange method. Alright, so these are the three ways in which deadlocks can be handled. Now let us go into a bit more of detail of these three methods and see how they work. So coming to the first method, which is the deadlock prevention or deadlock avoidance. So there we have discussed and said that we are trying to prevent or avoid deadlock in the first place itself, so that we don't need to deal with deadlocks in the future. We want to ensure that the system never enters a deadlock state. So in order to achieve that, we can either use a deadlock prevention or a deadlock avoidance scheme. So let us see what is deadlock prevention and deadlock avoidance, and what is the difference between these two, and how can we achieve these two schemes. So the first one is deadlock prevention. So in deadlock prevention, it provides a set of methods for ensuring that at least one of the necessary conditions cannot hold. So when we have discussed about the necessary conditions that must hold for a deadlock to occur in the previous lectures, I have talked about these four conditions: mutual exclusion, hold and wait, no preemption, and circular wait. So when we have discussed about that, we have seen clearly that when a deadlock has to occur, these four conditions must hold simultaneously. Only if these four conditions are all holding, only then a deadlock can occur. So if at least one of these conditions cannot hold, then we can ensure that there will be no deadlock, because deadlock can occur only when four of these conditions hold together. So if at least one of them cannot hold, then we can ensure that there will be no deadlock. So that is what we do in a deadlock prevention scheme. So this is just a brief idea about the deadlock prevention. So we'll be discussing in detail about this in the following lectures. Alright, so now let's come to the second one, which is deadlock avoidance. So in deadlock avoidance, it requires that the operating system be given in advance additional information concerning which resources a process will request and use during its lifetime. With this additional knowledge, it can decide for each request whether or not the process should wait. So in deadlock avoidance, what we are doing is we need to give the operating system some additional information in advance about what are the resources that a process will request and use during its lifetime. That means during the course of its full execution, what are the resources that a process will require. This information should be given in advance to the operating system. And if the operating system is having this information in advance, it can prevent deadlocks from occurring by taking care of the way resources are allocated to processes. So when we saw about resource allocation in the previous lectures, we saw that a process begins its execution and it asks for some resources that it needs, and then in the course of its execution it needs some more resources and it requests the operating system for those resources again. So whenever it is going to request for some new resources, the operating system does not know in advance which are the resources that the process is going to require. But if the operating system already knows which are the resources that a process will need during the course of its lifetime, then we can avoid deadlocks. So deadlock occurs when the operating system does not know which are the resources a process will be requesting in the future, and then when it requests for that resources, let's say that that resource was being held by some other processes, which in turn is also waiting for some other resources, and the cycle goes on. We have already seen that, and that is how deadlocks occur. But if the operating system knows in advance, it can plan and it can allocate the resources in such a way that deadlocks can be avoided. So that is what we mean by the deadlock avoidance scheme. So in deadlock prevention, we are making sure that at least one of the four necessary conditions does not hold, and in deadlock avoidance, we are giving the operating system in advance the additional information about what are the resources a process will need during its lifetime. So this is how we can handle deadlocks using the deadlock prevention and the deadlock avoidance schemes. So this is a brief introduction to these two schemes. They are actually larger topics and we'll be discussing them in the coming lectures. Alright, so now we have an idea about the first method, which is deadlock prevention and deadlock avoidance. Now let's go to the second method. So in the second method, if a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, then a deadlock situation may arise. So the first method was to prevent or avoid deadlocks. So in the second method, we are assuming that there is no deadlock prevention scheme, nor there is a deadlock avoidance scheme. So if we don't have these two schemes, then there could be a situation where a deadlock can arise because we are not preventing it, nor are we avoiding it. So in this case, a deadlock situation may arise. So when it arises, what are we supposed to do? So in this environment, the system can provide an algorithm that examines the state of the system to determine whether a deadlock has occurred, and an algorithm to recover from the deadlock if a deadlock has indeed occurred. So in this kind of a situation, what we can do is the system can provide an algorithm that examines the state of the system to determine whether a deadlock has occurred or not. So I told you it has to first detect if a deadlock has occurred or not. Our system may be in deadlock and we may not have a mechanism to detect a deadlock. We may not know that there is a deadlock even though there is a deadlock. So that should not happen. So in this, we first need to make sure that we have a mechanism to determine whether a deadlock has occurred or not. That means detection mechanism should be there, and after it has detected that there is a deadlock, there should be a mechanism or an algorithm to recover from the deadlock. So if a deadlock has indeed occurred, then the system must provide an algorithm to recover from that deadlock. So this is another solution that we have, or another method that we can use for handling deadlock. So the first method was prevention. The second method is cure. That means we allow the deadlock to occur, but we detect it and we are recovering the system from the deadlock. So this is the second method that we have. All right, now let's go to the third and the final method. So here in the third and the final method, if the system neither ensures that a deadlock will never occur, nor provides a mechanism for a deadlock detection and recovery, then we may arrive at a situation where the system is in a deadlock state, yet has no way of recognizing what has happened. So this is the final method that we have discussed, which is to just ignore the problem altogether and pretend that deadlocks never happened. So in this situation, what will happen? We don't have a deadlock prevention or avoidance scheme. So we cannot prevent or avoid deadlocks from happening in the first place. And if a deadlock has indeed occurred, we also don't have a method for detecting the deadlock. We don't know whether the deadlock has occurred or not. And if a deadlock has actually occurred, we also don't have a method for recovering from the deadlock. So the system will be in a deadlock state, and yet it will have no way of recognizing what has happened. So this is the final thing, or the final way deadlocks are handled. So in this case, the undetected deadlock will result in deterioration of the system's performance because the resources are being held by processes that cannot run, and because more and more processes, as they make requests for resources, will enter a deadlock state. So in this case, this deadlock will lead to the deterioration of the system because resources are being held by processes, and the processes are not going to release them because they are in deadlock, and other processes will again make requests for resources, which will also cause more and more deadlock state. And what will happen finally? Eventually, we cannot do anything. The system will be hanging, and then we will have to restart the system manually. So eventually, the system will stop functioning and will need to be restarted manually. So this will happen if we don't have a deadlock prevention nor avoidance scheme, and also if we don't have a mechanism for detecting and recovering deadlocks. So this may look like a very strange and useless solution, and we may even think, how is this a method for handling deadlock at all? But nevertheless, this method is also used by many operating systems because they assume that there will be very few deadlocks that can occur, and it is a responsibility of the application programmers to develop their applications in such a way that deadlocks do not occur by the processes that are there. So instead of investing and spending on deadlock prevention, avoidance, or detection and recovery, they feel that this may be a better option. So they may be using this method for handling deadlocks. So we see that this is a cheap way of handling deadlocks, but we cannot ensure that the system will be functioning properly every time. There may be times when deadlocks will occur, and if a deadlock occurs, then there is no way of recovering from it, and the system will stop functioning, and manual restart will be the only thing possible. So though this is a method, this may not be a very good method as well. So we have seen the three methods for handling deadlocks, and the most important among them is the deadlock prevention and the deadlock avoidance schemes. So in this lecture, we have had a brief introduction about this, and in the following lectures, we will be discussing in detail about the deadlock prevention and the deadlock avoidance schemes and how they can be achieved. So I hope this lecture about the introduction to the methods that we have for handling deadlocks was clear to you. Thank you for watching, and see you in the next one. previous lectures, we have been studying about deadlocks. In the previous lecture, we have started discussing about the methods for handling deadlocks, and we have seen 3 ways that can be used for handling deadlocks. So there we had a brief introduction about deadlock prevention. So in this lecture, we'll be discussing in detail about deadlock prevention. So we'll be seeing how can deadlocks be prevented, what are the things that we need to do for preventing deadlocks. So for a deadlock to occur, each of the 4 necessary conditions must hold. So when we have studied about deadlocks, we have already seen that for a deadlock to occur, there are 4 necessary conditions that must hold, and they are mutual exclusion, hold and wait, no preemption, and circular wait. So we have discussed about these 4 conditions in detail in one of the previous lectures. So we have seen that only if all of these 4 conditions hold, only then the deadlock will occur. So if at least one of them does not hold, then we can say that a deadlock will not occur. So in deadlock prevention, what we are going to do is that we are going to try to make sure that at least one of these conditions does not hold, and hence we can prevent deadlocks from occurring. So let us see how we can do this. We'll be taking each of these conditions one by one, and we will be seeing if we are able to make at least one of these conditions not hold, so that deadlocks doesn't occur. So let's see and discuss these conditions one by one. So as I said, by ensuring that at least one of these conditions cannot hold, we can prevent the occurrence of the deadlock. So let us first see the first condition, that is mutual exclusion. So coming to mutual exclusion, let us just try to recall what was mutual exclusion. So in brief, mutual exclusion is a condition that when a process is making use of one resource, that resource cannot be used by any other processes. That means it cannot be shared by any other processes. So that is a brief idea about mutual exclusion. We have discussed it in detail before, so I'll not be going into the detail of it, but that is what mutual exclusion means. So in mutual exclusion, we see that the mutual exclusion condition must hold for non-shareable resources. So there are resources that cannot be shared by processes at the same time. For example, printer. A printer cannot be simultaneously shared by several processes. We know that when one printing is happening, there cannot be another printing happening at the same time. Only when the first document finishes its printing, we can go to the next printing job that is there. So we see that mutual exclusion condition must hold for non-shareable resources. So here, what is the main idea that we are talking about? We are trying to prevent deadlocks from happening. And for deadlocks to not happen, we should make sure that mutual exclusion does not hold. We are taking the conditions one by one and trying to analyze if we are able to make at least one of these conditions not hold. So talking about mutual exclusion, we see that mutual exclusion must hold for non-shareable resources. It is really not possible for us to avoid mutual exclusion, because for non-shareable resources, we cannot avoid mutual exclusion. Mutual exclusion has to be there. But in case of shareable resources, it's okay even if mutual exclusion is not holding. So shareable resources, in contrast, do not require mutually exclusive access and thus cannot be involved in a deadlock. For example, read-only files. If several processes attempt to open a read-only file at the same time, they can be granted simultaneous access to the file. A process never needs to wait for a shareable resource. So if it is a shareable resource, unlike a printer that we have talked about here, which is a non-shareable resource, if it is a shareable resource, then we don't need a mutually exclusive access. We don't need mutual exclusion. Like for example, read-only files. So in read-only files, only reading can happen from that files. Nobody can modify or write into those files. Those files are only for reading. So if different processes tries to read from the read-only file at the same time, there is no problem because they are only going to read. So we can allow as many processes as it requires for reading from the same file. It is not a problem. So this read-only files is an example of a shareable resource. So if it is shareable resource, then there will be no mutual exclusion. We don't need this mutual exclusion condition to hold, and hence they will not be involved in a deadlock. But in case of non-shareable resources like printers, we cannot allow more than one process to access this at the same time. So in case of non-shareable resources, mutual exclusion has to hold. So we see that mutual exclusion is a condition that we cannot totally avoid. So in general, however, we cannot prevent deadlocks by denying the mutual exclusion condition because some resources are intrinsically non-shareable. So here as a whole, what are we trying to do? We are discussing about deadlock prevention. And for deadlock prevention, we see that mutual exclusion is one condition that must hold for a deadlock to occur. But we are trying to see if we can avoid this mutual exclusion so that deadlocks will not occur. But we see that we cannot avoid mutual exclusion altogether because there are some resources that cannot be shared by different processes at the same time. So mutual exclusion has to be there. So we can say that mutual exclusion is not a condition that cannot be avoided, and hence we cannot prevent deadlock by avoiding mutual exclusion condition. So we see that mutual exclusion is not a condition that we can avoid. So hence mutual exclusion is out of the question. Mutual exclusion should be there. So deadlock prevention is not easy to be done by avoiding mutual exclusion. So that is what we understand by this. Alright, so now let's go to the second condition. So the second condition that we have is hold and wait. So what was hold and wait? So hold and wait was a condition where a process is requesting for some resources, and when it is requesting, it is also holding some other resources. So a process is holding some resources and it is waiting for some other resources. So that is what we mean by hold and wait. And hold and wait is another condition that must be there for deadlock to occur. So we are trying to see now if we can avoid this hold and wait so that deadlocks doesn't occur. So to ensure that the hold and wait condition never occurs in the system, we must guarantee that whenever a process requests a resource, it does not hold any other resources. So this is the main thing here. In order to avoid hold and wait, what we have to do, we have to ensure that when a process is requesting for another resource, it must be sure that that requesting process is not holding any other resources at that time. Only when a process is not holding any resources, it can request for a new resource. So if we can fulfill that condition, we can make sure that hold and wait condition will not be there, and hence we can avoid deadlock in that way. So let's see if we can achieve this and if this is a good solution. So one protocol that we can use for achieving this is given here. So let's see. One protocol that can be used requires each processes to request and be allocated all its resources before it begins execution. So here what we are trying to do is, before a process begins its execution, it has to request all the resources that it is going to require during the course of its execution, and it must be allocated all the resources before it begins its execution itself. So we saw that in normal ways how it was happening is a process begins its execution and then it requests for some resources, and later on it needs some other resources, so it makes a new request, and then if it is available, the resource is allocated to it, and then it goes on like that. But here this protocol suggests that before a process begins its execution, all the resources that a process will ever need during the course of its execution should be requested before the execution begins itself, and it must be allocated to the process before the execution begins. And until and unless it gets all the resources, it will not begin its execution, and only after it gets all its resources, it will be beginning its execution. So for example, let's say that there is a process that requires the disk drive and the printer. So the disk drive and printer are resources. So let's say that it first needs to use the disk drive and later on it needs to use the printer. So instead of requesting them separately, afterwards, what it will do is, before it begins its execution itself, the process will say that I need the disk drive, I need the printer. And these two things will be allocated to that process. And once it is allocated, the process will begin its execution, and it will first use the disk drive, and at that time the printer will be there with it, and later on when it needs to use the printer, it will use the printer. So we see that the process will be having all its resources, and only then it will begin its execution. That is one protocol. Now let's see another protocol. So here, an alternative protocol allows a process to request resources only when it has none. A process may request some resources and use them. Before it can request any additional resources, however, it must release all the resources that it is currently allocated. So this is another way to go around it. So here it says that whenever a process wants to request a resource, it will be able to request only when it is not holding any other resources. That means only when the process is not having any resources with it, it can request for another resource. So a process may request some resources and it may use them, but before it can request any additional resource, it must be releasing all the resources that it is holding, and then it will be able to request for the new or the additional resource and then get hold of it and continue its execution. So let's take an example again. Let's say that a process is currently holding the disk drive and the printer. It is holding the disk drive and the printer and it is doing some execution, and it needs a new resource now, which is the memory. Let's say that it needs to make use of the memory. So before it requests for the memory, it needs to first release the disk drive and the printer that it is holding. So only after it releases the disk drive and the printer, it will be able to request for the additional or the new resource, which is the memory. So in this, we are making sure that whenever a process is executing, it is not holding something and waiting for something else. In the first protocol, we see that if the process is already allocated all the resources, it will hold all the resources, but it will not be waiting for any other resources because it already has what it needs. So it can just continue its execution smoothly. And in the second approach, we see that whenever a process is going to request for a new resource, it is going to release what it is already having. So this holding is not happening. It will first release everything and then only it will request for a new resource. So we see that hold and wait can be avoided by following either of these protocols. But is this an efficient way of handling it? So here we see that both of these protocols have two main disadvantages. And what are they? It is resource utilization may be low and starvation is possible. So let's see why are these two disadvantages present. So here, first of all, resource utilization may be low. So let's see here. In the first protocol that we saw that a process is going to first get hold of all the resources that it needs and then only it will begin its execution. So let's take the first example again. So I said that there is a process which needs the disk drive and the printer. So it will first ask for both the disk drive and the printer, and it will acquire both of them, and it will be keeping both these resources with it, and then only it will begin its execution. So let's say that first of all it is using the disk drive. So when it is using the disk drive, the printer is remaining idle. So it is holding the printer and keeping the printer with it, but the printer is remaining idle because it is right now using the disk drive. So we see that resource utilization is low here. The printer, if it was not being held by this current process, it could have been used by some other process which needed to use the printer. So we see that resource utilization is low here. This is one of the disadvantage. And here the second disadvantage is starvation is possible. So starvation could occur here. Like for example, in this second protocol, we see that when it needs to request for a new resource, it has to release the resources that it was holding. So let's say that it released it, but it also needed that resources in a later time. But since it has already released it, there will be another process that now gets hold of those resources and are holding it. Now this process which has currently released it, let's say that it needs those resources back again. So it is going to request for them again by releasing what it just finished using, but it is being held by some other processes. So there we see that starvation is possible. So even in this one, we see that starvation could be possible in the first scenario. Even in the first protocol, we see that one process will be holding all the resources it needs. So there may be other process that also needs the same resource, but since it is being held by that first process, it is not able to get it. It may end up waiting for a long time. So starvation could occur here. So this is another disadvantage of this protocols. So we see that we can avoid hold and wait by following this kind of protocols. It is possible to avoid it, and hence it is possible to avoid deadlocks by preventing this hold and wait from occurring. But we also see that it is not a very good solution because these protocols are having disadvantages. The resource utilization is low and starvation. So these kind of disadvantages will be there, though it is possible to avoid deadlocks by avoiding the hold and wait. Alright, so that was the second condition. Now let's go to the third one. So the third condition is no preemption. So what is preemption? So preemption is when a process is making use of some resource, no other process can take away that resource from that process which is currently using it. That is what we mean by no preemption. So no preemption is another condition that must hold for deadlock to occur. So what we want to prevent deadlock. So for preventing deadlock, we want to see if we can avoid no preemption. So if we are avoiding no preemption, what does it mean? It means preemption should be there. So the opposite of no preemption is preemption. So that is what I mean here. So let's see if we can achieve this. So to ensure that this condition does not hold, there is no preemption, we can use the following protocol. So let's see what is this protocol. If a process is holding some resource and requests another resource that cannot be immediately allocated to it, that is, a process must wait, then all resources currently being held are preempted. So here what it says is, if the process is holding some resources and at the course of its execution, it is still holding those resources and it needs some other resource, and it is making a request for that new resource. But let's say that that new resource that it requested is not currently available at the moment, and hence the process has to wait. So if such a scenario arises, then that waiting process will have to release all the resources that it was currently holding. That means all the resources that are currently being held by that process will be preempted. So it will be released from that process. So if a process is requesting something and it is not getting it, then even what it was already holding will be preempted or taken away from it. So that is what we mean by this protocol. So here we see that preemption is happening. So if this preemption is happening, what will happen? The process will not keep waiting for the new resource by holding its previous resources, but it will release everything. And if it releases everything, some other processes can make use of those resources. So that is what we mean by this protocol here. Also, we can go around in this way. Alternatively, if a process requests some resources, we first check whether they are available. If they are, we allocate them. If they are not, we check whether they are allocated to some other processes that is waiting for additional resources. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. So this is another way to go around this. So here what happens is, let's say that a process is requesting some resources. So first of all, we will check if the resources are available. So if it is available, it will be allocated to that process, well and good. But if it is not available, we will check if those resources that was being requested by this process is held by any other process which is also waiting for some additional resources. Then what will happen? If we see that such a scenario is there, then we will preempt the resources from that other waiting process and allocate it to the first process that is requesting it. So I hope that is clear. So let's say process P1 and P2 are there. So let's say P1 is requesting some resources, R1, R2 and R3. And let's say that it is currently being held by process P2. R1, R2 and R3 are being held by process P2. And P2 is also waiting for some other resource which it has not got till now. So what will happen? We will preempt resources R1, R2 and R3 from P2. And we will allocate it to P1 which was requesting it. Because P2 is anyway waiting. So we are taking away whatever it is having and giving it to P1 so that P1 can do its execution. So in that way we see preemption is happening, and in that way we can prevent deadlocks from occurring. So we see that these are the two ways in which we can make sure that the no preemption condition does not hold. That means we are making sure that preemption is happening, and hence we are able to avoid deadlock. So if we are able to avoid preemption, then also we see that we are able to avoid deadlock. But again, let's see if this is also a good solution or not. So here, this protocol is often applicable to resources whose state can be easily saved and restored later, such as CPU registers and memory space. It cannot be generally be applied to such resources as printers and tape drives. So this method is easily applicable only to those resources whose states can be saved and restored later, like CPU registers and memory space. And why is that? That is because, let's say that a process is making use of a resource, and if preemption happens, when it is preempted, we are not sure that the process actually finished using the resource. It may be in the middle of using that resource, and if we are taking the resource away from it, then we need to save the state of that process. We need to have a record of up to where did that process use that resource, up to what state, so that when the process gets back that resource, it will be able to resume from that point. We should be able to save the state of the processes. So only resources whose states can be easily saved, like CPU registers and memory spaces, can be applicable for this method. So it is not generally applicable to resources like printers and tape drives. So let's say that a process is using a printer, which is a resource, and it has printed half of the document, and at that time it is being preempted. The printer is taken away from it. So we see that it is left unprinted up to the half, and we may not be able to start printing from the half of the document again. You may be able to manually do it, but automatically it will not be done. So we see that for resources like printers and tape drives, this preemption cannot work. So we see that it is possible to do it, but it is not applicable for resources like printers and tape drives. So this is another disadvantage that we have if no preemption is not holding. So that is the third condition that we have for preventing deadlocks. Alright, now let's go to the fourth and the final condition. So the fourth and the final condition that we have is circular wait. So what was circular wait? So in circular wait, we see that process P1 is requesting for a resource R1, and resource R1 is being held by process P2, and P2 is waiting for another resource which is being held by process, let's say P3, and P3 is again waiting for resource R1, which in turn is being held by P2. So we see that there is a circle. They are waiting in a circular fashion. One process is waiting for a resource which is being held by another process, and this process is waiting for another resource which is held by this process, and this process here is again waiting for another resource which is held by the first process that we talked about. So it is forming a circular waiting pattern. So this is another condition that must be there for deadlocks to occur. So if we are able to avoid circular wait, then also we can prevent deadlocks. So let's see how we can prevent this circular wait from happening. So a way to ensure that this condition never holds is to impose a total ordering of all resource types, and to require that each process request resources in an increasing order of enumeration. So this is what we can do in order to avoid circular wait. So this may seem a bit confusing, but we'll make it clear. So it says here that we need to impose a total ordering of resource types. That means all the resources that are there will be given some order. We will be numbering it using some numbers. So let's say that we have 5 resources, and we number them as resource R1, R2, R3, R4, and R5. And we will require that each process will request resources in an increasing order of enumeration. That means if process P1 is requesting for resource R2, let's say, then it will be able to request next resource in only an increasing order of enumeration. That means it is requested for R2. So the next resource that it requests should be having a higher number than R2. That means it should be either R3 or R4. It cannot request for a resource that is having a lower number. That means it cannot request for resource R1. So that is an example. So here let's take another example. Suppose process P1 is allocated resource R5. Now, if P1 requests for resources R4 and R3, which are lesser than R5, such requests will not be granted. Only requests for resources greater than R5 will be granted. So if P1 is allocated R5 and it needs R4 and R3, so we see that 4 and 3 are lesser than 5, it will not be granted. Only if the requested resource is greater than R5 in number, then only the request will be granted. Now keep in mind that this numbering is something that we are giving. So we will be giving numbers to resources like R1, R2, R3, R4, R5. Now, if we don't allow a process to get a resource that is lesser in number than the one that is holding, then the circular wait will not happen. So we see that if this kind of numbering is given, and if processes are allowed to request for only resources that are in increasing order of enumeration or numbering, then we can see that the circular design or pattern will not occur here. So the circular wait will not hold if we follow this kind of a protocol. Alright, but is this method also a good way of preventing deadlocks? Let's see. So here it says, developing an ordering or hierarchy in itself does not prevent deadlock. It is up to the application developers to write programs that follow the ordering. So we see that just by giving numbers to the resources like R1, R2, R3, R4, just by giving the numbering, we are not going to prevent deadlocks. Only deadlocks will be prevented if the application programmers develop their applications in such a way that this rule that we mentioned here will be followed by their applications. So the request for resources will be granted only if they are requesting for resources in an increasing order of enumeration. So this must be designed by the application programmers in such a way that their applications will be working in this way. Just by giving our numbering, it will not prevent deadlocks. So the application programmer has to make sure that his application works in such a way that the processes will be granted resources only if they are asking for resources in a increasing order of enumeration of the resources. So this is what should be followed in a circular wait. So if we are able to do this, and if the application programmers also cooperate and develop applications in such a way, then we can avoid the circular wait, and hence we can prevent the deadlock. So this is another method that we can use for preventing deadlock. So we see that for deadlock prevention, we need to make sure that at least one of the conditions, that is mutual exclusion, hold and wait, no preemption, or circular wait, one of them should not hold. And we saw how we can avoid each of these conditions using different methods that we have discussed. And we have also seen that some conditions can never be avoided. And we also saw that there are disadvantages when we avoid some of these conditions. So though this is a way for deadlock prevention, it has its own disadvantages, and also there are times when it cannot be done. So this is the way deadlock prevention can be done, by avoiding one of these conditions, and this is the way how each of these conditions can be avoided. So I hope this lecture about deadlock prevention was clear to you. Thank you for watching, and see you in the next one.